Welcome to this video on partial fractions decomposition. I call these type 2 problems where the denominator has an unfactorable quadratic in it. You'll notice that x squared minus 3 is quadratic, has an x squared in it, and also doesn't factor. The process for decomposing this into two fractions here is similar to type 1, except for the numerator above the unfactorable quadratic. You'll notice that the second fraction has a linear numerator with two unknowns, p and s. You set up a linear numerator like this anytime you have an unfactorable quadratic in the denominator. But from here, the process is essentially the same. What we're asserting when we write this second line is the following. We are saying that there is some number g, some number p, and some number s that will make these two expressions. So the best way to go about finding the values of g, p, and s are condensing this two fraction sum into a single fraction. So I will use the multiply by 1 trick twice. Notice the blue thing is a 1 and the orange thing is a 1. I'll use this trick twice to get a common denominator. I'll work out the numerators. The algebra is a little messy, but it's something you can handle. And then I'll combine my numerators over a common denominator. But notice when I combine my numerators, I've in some sense rearranged the order of them so that I have my x squared terms first, followed by my x terms, followed by my constants or non-x terms. The reason for this rearrangement is just to make it easier on me mentally. Remember, we want all these expressions to be equivalent to each other. The only way that they can be equivalent is if the numerators are equivalent. And so I need these two terms in red at the bottom to combine to make 3x squared. The only way that can happen is if g plus p equals 3. That's my first of 3 equations that I'm going to use to solve for g, p, and s. Secondly, the only way these expressions can be equivalent is if the two x terms in the bottom combine to make negative 4x. And therefore, it must be true that p plus s equals negative 4. And thirdly, the only way these expressions can be equivalent is if the constant terms on the bottom add up to negative 11, thus creating my third equation here. And now that I've created these equations, I ignore the entire algebra problem that led to this system of equations and just solve the system of equations on the bottom. Now, this video is not about how to solve systems of equations, so I won't go into the algebra, but I will show you the end result. I solved this system of equations and found the values of g, p, and s. Algebra not shown here, but let's proceed. So what I've proved is that if g is 2, p is 1, and s is negative 5, then all of these expressions are equal to each other, and most notably, the two expressions at the top are equal to each other for those particular values of g, p, and s. So now watch the second line as I convert g, p, and s into their newfound values, and I'm done with this problem. By the way, that 1x you see in the answer, bothering me a little bit because 1 times anything is itself. So I can simplify that, and now I'm finished. And thank you for watching this video.